Hello everybody, welcome to this video. This video is to teach you about shear stress distribution in beams, and basically you're going to be seeing how shear stresses in a beam can be calculated, how they vary through the cross section of the beam, and how they vary depending on what the cross section of the beam is. So the first thing that we would like to look at is that if you have a beam undergoing bending under some general load, you know that it's going to probably bend in such a curvature fashion. And if when you take any 4 points on this beam A, B, C, D, uh, lying on either side of the neutral axis of the beam, then you know that no, the after deformation, uh, these 2 points A and C, which were on the same line before deformation, now after the beam bends, they are going to move apart by a certain distance uh, depending on the curvature of this beam after it has bent. So we see that still this line will have a 90-degree with the neutral axis. So you just magnify it and see it in a larger scale. You see that after deformation, the line joining A and C, they will still remain straight, and this will be just depending on the curvature of the beam, or the radius of the curvature of the beam. Now let's look at a different case where now in this beam which I've shown here, this whole section is not it's not a homogeneous solid. It's not. I would rather say this is not monolithic, meaning that it's not the same. It's not fixed together. Okay, it's not pasted together. So all these parts, they're all you know you know strips which are not lamin, which are not bonded. So these are strips which are not bonded. Now when I stack such four strips on top of each other, and when I subject it to the same bending load, I see that instead of deforming as a single entity, I see that each of the strip is going to bend on its own. Okay, each of the strips is going to bend separately. Okay, so this is what happens. And now if I just take two of those strips together, and I look at and I if I take points on these two strips. Okay, now after they undergo bending, I will find that now in case if you look at a monolithic beam, you see that whatever A is, it's going to lie on the same radius of the curvature. A and C will lie on the same radius of curvature since they were on the same line before bending. Now in this case, two lines which are on 2 points which are on the same line before bending. After bending, what will happen is, since now what has happened is these 2 points are not, I mean these two strips are not bonded to each other. So this bends separately, this bends separately, and therefore when it undergoes bending, I will see that the point A, when the two strips undergo bending, this point C will not move along with the point A, and it will not lie on the same radius of curvature. Rather, it will lie on the same point. It will lie along the same vertical line on which A lies. So if it was bonded, this point C should be over here. But now since it is not bonded, instead of being here, the point C still lies right below right below A. The point C, instead of moving this way as the curvature of the beam is increasing, instead of doing that, it is still going to lie on the same point C, depending because now C and A are not bonded to each other. So what we can say is this this point C should have been here, but it's not over here anymore. It's lying at some other point, and this point and this distance where it should have lied, but now where it is actually lying. So this is something like the distance over which the two strips slide over each other. So this is the sliding distance between the two strips. So It is something like you have two strips and they are not bonded to each other, so one is sliding over the other. So this is the distance over which the two beams are sliding over each other because there is no bonding between them. Okay, so now what we can go to is, we know that in case we have a simply supported beam subjected to some point load, this is going to be our bending moment diagram. And let me say that I have some moment over here and some moment over here. Okay, all right. And this is the cross section of the beam, and the neutral axis lies right through the center. Now what I'm doing is I'm going to just kind of cut out this beam into two parts, part 1 and part 2. Okay, I'm cutting it into two parts, part 1 and part 2. And by the way, this is oh, by the way, this is not the cross section. This is the part of the beam between these two parts. Okay, so this is the part. This is just a segment of the beam between A and B. So this is a segment of beam between moment points M1 and M2. Okay, it is the part of the beam uh, lying between these 2 points. Okay, it is a part of the beam lying between here. And so here the moment is lesser, which means the stresses on this side of the segment will be lesser. Here the moment is more, so the stresses on this side of the segment will be more. So in what I mean to say is sigma AC will be greater than sigma BC, and sigma AT will be greater than sigma BT, C and T for compression and tension. Okay, so now the total force in segment A, the left side of segment A, the force, let me call this as FA1, equals nothing but, so let me call this point M, let me call this point M. Okay, so in M, so this is nothing but sigma 8, the stress at point N plus stress at point N. It's a trapezial distribution of stresses between these 2 points. So the total force lying within this is the area of the trapezium. Okay, so G into B. All right. So this is the total force in the on this part, and similarly on this part, I say if B1 equals sigma BTM plus sigma BTN by 2 times G times B. Okay. Now, since we know that sigma AT is greater than sigma BT, FA1 will be lesser than FB1. FA1 will be lesser than FB1 since M1 lesser than M2. Okay. So, which means FA1 minus FB1 is not zero, and therefore no equilibrium along X. There is no equilibrium along X, which means there is a force needed for it. Equilibrium. Okay, there's a force needed for this equilibrium. So how I see that is, now if I have a look at this, so this is the side A, this is the side B, which I have talked about here, and so this is the part above the part 1, the part sorry, the part so there's two parts, part 2 and part 1. So imagine that this is part 2 and this is part 1 as described above. So this and this are not equal. So there should be some force in the horizontal direction that can make sure that there is some equilibrium along the x direction. So that force is your shear force. So that force is your shear force, which, since FA1 is lesser than FB1, the shear force is going to act along the direction of FA1 so that it counteracts the FB1 force. So this is your shear force, and this will also have a component on the uh, direction adjacent to it. Okay, this will also have a component in the adjacent direction. And another thing which it is interesting for you to notice, if you have a beam like this which is having a constant bending moment diagram, then any two points that you take, any 2 points that you take on the bending moment diagram or on this beam, they are going to have the same bending moment, which means your sigma A and sigma B will be the same value, therefore leading to, you will get FA1. This will give you FA1 equals FB1, which means it's alternate equilibrium and you do not need an additional force to cause equilibrium. Therefore, your shear force anywhere here will be zero, and that's how you get a constant shear force diagram for this. Okay, and so this is how the shear force comes into the picture. And any beam that you take, if you isolate out a small component, so you have seen that now this shear force over here is caused so that the FA1 and FB1 are balanced. Okay, this shear force is caused so that FA1 and FB1 are balanced with each other. But in general, you will find that in any element you will find that shear forces or shear stresses will exist in pairs which are complementary in nature. Complementary in nature. So even though what we have discussed about talks about this shear force alone, these two cannot exist alone. If only this, if only these two exist alone, let's say that only these two exist alone. If only these two exist alone, this will cause a couple. This will cause a couple, an additional couple, and this will lead to loss of moment equilibrium. So therefore, to prevent the loss of moment equilibrium, you will have additional shears developed, which will counteract the couple caused by this and this, and now you will have moment equilibrium, and therefore this will make sure that moment equilibrium is maintained. Okay, so what we would like to state over here is, therefore we can make the following statements about shear force. So shears can be visualized in two ways. Okay, one which is one that arises out of vertical force equilibrium, as usually done for beams. So what I basically mean is, for example, at each section we say that the shear force is nothing but, say, VA minus Q of X. If we had a situation or a beam like this, we would say, so if this was our VA and we had some Q of X, then we would also be able to find out this shear force. Okay, so this is the general way how we find shear forces for beams, and so this is one way of visualizing the shear forces. And of course, the second way of visualizing shear forces arises out of horizontal force equilibrium due to the normal stress differences at either side of a segment. So basically, this is what was discussed above. Okay, so what we say is no, these two uh, are the two ways in which shear forces manifest each other, but they complement. So, but they complement each other. Okay. Another thing that you can also notice is now if you have a look over here, uh, so I've taken a section between this point and this point. The segment is between these 2 points M and N. And for this, I would have gotten a certain value of Fa1, a certain value of Fp1, giving me some certain value for the shear force, some value of the shear force that is required to cause equilibrium between these two. Now, in case I had taken a section over, say I've taken the section over here, okay, then I will have a different value of Fa1 and a different value of Fb1, and therefore my shear force will also become different, and this tells me that the shear forces or the shear stresses will be different at different uh, locations along depth. Okay, so this is very similar to how you found for this is very similar to normal stresses. It's very similar to normal stresses which vary, as you know, along the depth. Okay, which vary along the depth. Now another thing we can notice is, now if say that I want to find the shear force at this surface. Say that we need the shear force at this surface. Now, what is the value of Fa1? So Fa1 is sigma ATM plus sigma 18 by 2 plus G times B. And at the surface, G tends to 0 at surface. Okay, G tends to 0 at the surface because it is right at this point. Okay, so this will give you Fa10 and Fb10, and therefore shear force will also come as 0. So therefore, at surfaces, shear stresses, or rather shear forces, will be equal to 0. Tau, the symbol which we use for shear stress, will be 0. Okay, and also we know that it also varies along the depth. So therefore, simply saying tau equals to shear force by area is only your average. Okay, this is what we normally do. Any design of a beam that we do, either in concrete or steel, we even in steel there are some specifications about this area, but especially in rectangular concrete beams, we just simply do tau equals V by A. That tau is only the average shear stress. It's not the maximum shear stress. It is minimum somewhere, maximum elsewhere. Okay. So we generally use the tau average because finding exact shear stresses is not very simple. Okay. So it's not very simple, and let's see why we give such a statement. Now look at this cross section of the beam. Okay, so look at one cross section of the beam at, separated by a distance dx. So I've taken a certain strip near the top. That strip is located at y from the distance from the neutral axis, and this is the distance to the top fiber. So there are two stresses, sigma x1 and sigma x2, caused by the moments mx at A and mx plus dm by dx into dx at B. So these two are the moments causing these stresses, and thus and the element is dx in length. Now this is along the span. So this dx is once again, as I told before above, a long span. This is not the cross section. And the cross section is shown over here, a random cross section. So I see that my shear stresses will act on along the along the span direction. My normal forces are acting on this element, on this small element dy. So this small element is, so the small element dy located y above the neutral axis, top fiber once again yt above. This is my tau xy, and this tau xy is acting over a span dx. The same tau xy is shown over here. Okay, and this sigma x2 etc. No, that is this red arrow marks. That is the sigma x2 or sigma x1. And I've taken a very general section such that the thickness varies along the depth. Usually you won't have the case, but let's just assume that the thickness varies along the depth. So therefore, I say T of y rather than just simply saying T. Okay. Now what I can do is I can write force equilibrium equation along the horizontal direction. So I can say now sigma fx equal to 0 implies, now, so this is the, now what I can do is I can, so I take an element of thickness dy. It's located over here at a distance y from your neutral axis. So I'll say y to y top. Okay, yt equals sigma x1 times t of y dy minus y to y top sigma x2 t of y dy plus tau xy ty dx equals 0. So t of y into dx is nothing but your area of I mean t of xy into dx is your shear at this point, and this here acts along this much width t of y. So t of xy into dx, which is this much, times how much ever thickness uh, t of y. Okay, so I'll just rewrite this, rewriting using flexure formula to convert my stresses into in terms of the moments. Okay, so integral y to y top, so m of x by I into y times t of y dy minus minus integral y to y top m of x plus dm of x by I into y into t of y dy plus tau xy t of y dx equal to 0. Okay, so now cancelling out the common terms, simplifying this whole expression, I get tau xy equals dm of x by dx, okay, into 1 by I and then this ty comes to the denominator, t of y. And also I see that both these integrals, this integral and this integral, all of them are integral over y. M of x does not depend on y, so I can keep this outside the integral. So y to y top, right? Y into t of y dy. Okay, so y into t of y dy. Right now, this y into t of y, if you see, it is nothing but y into t of y is nothing but the area of this elemental. I mean, it's this elemental area. Y into t of y is the area of this elemental area. So this is something like, so if I say y of, this is something like saying integral of a dy, which is actually nothing but first moment of area about Cg of area. Okay, this is nothing but the, so this whole thing is nothing but the first moment of the area about the Cg. So I can just give it another name. It can be called as Q. We also know V of x is nothing but dm of x by dx. So therefore, tau xy is nothing but V of x into q of q is dependent on y by I into t of y, and usually we will see that t will be constant. Q of q will usually be dependent on along the depth what is the position. So we can just omit these indexes and we can say vq by it, and this I should be ixx if you're doing vertical shear forces, and Iyy if you're doing uh, the other shear forces. Okay, so anyway, to avoid confusion for now, let us just omit this subscript. Okay, let us just omit the subscript. Let's look at an example of a rectangular cross section. Okay, let's have a look at a rectangular cross section. What we get as the expression for tau of xy along the depth. Okay, so we see that the shear forces are of value v, height of the or the depth of the cross section h, width of the cross section b. So any element taken at a distance y, and the area of this whole segment is a. So anyway, so integral will be doing this integral y to y top. So integral y to, so here to here is nothing but h by 2. So integral y to h by 2. Y top is at a distance h by 2. Y, which is this distance. So what is q? Q is nothing but y into t of y dy. T of y, it's not t of y here, it's a constant thickness b. It's a constant with b, so I can just say b into dy. So this gives me b y square by 2 between y and h by 2. So therefore, this comes b by 2 into h, this b by 2 into h square by 4 minus y square. This is the value of q, or the expression for q. This is the expression for q. We can go a little further and can find out what is, we also know ixx is bh cube by 12. So tau vq by I, instead of t we say b because we're using the width as b. So v into b by 2 h square by 4 minus y squared by bh cube by 12 into b Okay, so simplifying this, we get 6v by bh cube into h square by 4 minus y square. So it is y square. So this means this is a parabola. So this expression is a parabolic expression for a parabola. So therefore, I see that my shear stress distribution along the depth for a rectangular section is a parabola. Okay, it is a parabola. If I substitute, here it's h by 2. Okay, the y equals h by 2 here. So if I put h by 2 here, this expression becomes 0 and I get 0. Similarly, for this point, it is minus h by 2. Substitute minus h by 2 here, again you get tau equals 0. Now, at the middle, at mid height or mid depth, y equals 0. So this gives me tau equals 6v by bh cube into h square by 4. Simplify this, you will get 1.5 v by bh. We also known that tau average is nothing but v by cross-sectional area, which is bh. So therefore, tau max, the maximum tau at y equals 0 equals, so this is 1.5 times tau average, 1.5 tau average. So this is how the shear stresses in different cross sections can be found. So in this rectangle section, it is quite simple. If you have more complicated sections like something like cross sections like this or cross sections like this, you will have the calculations will be a little more complicated. But anyway, it can be done. It's not impossible. Your shear force diagram for this cross section, for example, I mean, this thickness is this depth is small. This depth is quite large. Okay, so depending on that, your shear stress distribution shape will change. Let me just make it neater. So this is quite different. So these are small. The web depth is bigger, and you may mostly be end up getting up a shape like this. So each element, the flange has its own parabola. The web has its own parabola. Okay, so you'll get a kind of a shape like this. So anyway, so this concept of shear stresses. It is here. How did you show it? You show that it's kind of flowing across this depth. It's flowing. So this is a cross section, and your shear is flowing downward. Your shear stresses are going downward. So in shapes like this, no, it is not. It cannot. I mean, you can imagine that the shear forces will be flowing downward here. Okay, but when it comes to shear stresses, you have to imagine shear forces as a flow. So you have to imagine shear as a flow. Okay, you have to imagine it as a flow, and if it has to flow, then this has to continue, which means the shear here, the flanges would actually be like this, and here it would be like this, and similarly here it would probably be like this. So this is known as shear flow, and this concept will come very useful in the calculation of an important geometric property known as important geometric property called as the shear center. So we'll see about the shear center in our next video. I hope this video was useful enough for you to have a better understanding of shear stresses. See you in the next video. Thank you.